Welcome to Space Talk. This is a special edition. My guest today is Jessica Barnes. She's an assistant professor of the Lunar and Planetary Laboratory at the University of Arizona. And she examines extremely rare samples of celestial bodies. Welcome, Jess.
Thank you.
Jess, in October 2020, about 200 million miles away from Earth, a spacecraft named OSIRIS-REx touched down on an asteroid named Bennu. Mm-hmm. What happened at that moment?
So we didn't actually touch or land on the asteroid. Instead, what we did was pogo stick. And if you're familiar with the children's toy that you jump around on with a very small surface area and you ping pong along the surface, we expected to do that, to just touch the surface and back away. But Bennu's surface actually ended up being a lot more porous and less resistant than we expected. And so instead of just touching the surface and backing away, we actually went 50 centimeters into the subsurface, so half a meter. And it was only when we fired the thrusters that we were able to actually back away. And there's some speculation, if we didn't do that, we would have maybe gone deeper or maybe all the way through the asteroid. Wow. It was very low resistance material. But we collected a sample, which was the important thing.
So when we watch a science fiction movie, usually when a spaceship lands somewhere and they got some material from there, it looks very easy. So it isn't very easy to take samples from an asteroid.
Space in general is hard, and with OSIRIS-REx, like many missions, there were lots of hiccups and bumps in the road. One of the bumps that we encountered was not so much collecting the sample, but when we turned the sampler head to look at the spacecraft and take a photograph, we realized that we had collected samples, so the team was very happy, and then we suddenly were mortified because we realized that we were losing material. So from the collector head, we could see dust particles flying out, and we realized that there was one big chunk of space rock, of Bennu, stuck in this flap that was supposed to keep all the material in, and instead it was leaking material out. So we overcame that by quickly putting the entire sampler head safe in its canister and then closing the sample return capsule. But it was one of those things that we weren't necessarily expecting, but we were then hopeful we'd saved enough material inside that we would have something to look at here on Earth.
So not that easy, and sometimes some sweat on...
Some surprises, yes.
Yeah. So, but finally the capsule came back to Earth. It landed with a parachute. How was that landing?
Terrifying. The release from the spacecraft was fine, and initial descent through the atmosphere all went swimmingly. But there were two parachutes that were supposed to deploy. First, a drogue parachute to really slow down and change the direction of the SRC, the sample return capsule. And then the second, the main parachute that would enable us to land very softly on the Utah desert floor. The drogue parachute did not deploy properly, but thankfully the main parachute did, and it all went smoothly in the end, and the sample return capsule just very gently plopped down on the sand in the Utah desert. So it worked out fine, but did not go according to plan. We were lucky.
So that was September 2023?
Correct.
And I read that the first samples could have been released in mid-January this year, in 2024, is that right?
So the team actually got a really quick sample within the first couple of days. So the sample capsule arrived on the 24th of September, and by the 26th or 27th of September, the team had a very, very small portion of the sample and had a couple of days to do some very quick analyses at NASA's Johnson Space Center. And then later in October, November time, some more of the team got some sample that they could then analyze. But we didn't get a look at all of the samples straight away. So there was a little hiccup with actually opening up the sampler mechanism that had the sample inside. And so we think it dates all the way back to assembly of the spacecraft and the components right back before 2016. It seemed like two of the screws were over-tightened, and so we couldn't actually get them out. So luckily, curation at NASA's Johnson Space Center are very smart, and they thought on their feet very quickly. And they knew that the flap that we had seen in space had that big particle that was allowing material to flow out of the sampler head. they realized that that flap is actually very flexible. So they were able to scoop out material, put it on trays, and then give some of that material to the science team, while the rest of the Bennu material was stuck inside until January, like you said, when finally NASA had developed some new tools with a bit more torque, a bit more, give to actually loosen those screws and then expose all of the material that we had collected from Bennu.
And I can imagine that you didn't do that just in a laboratory on a table, but it was in a very clean situation, right?
Exactly, and that's one of the challenges to bringing back samples with sample return missions. Is one of the challenges and the benefits, right? We go there because we can bring back materials that we keep pristine. We don't let them interact with Earth's environment, so we keep them in inert environments, either nitrogen gas or some kind of gas that doesn't have water in it. That means we can minimize any contamination or interaction or alteration from Earth's atmosphere. But that also means it's a challenge for those people actually working with the sample. It's not like I pick it up the sample and I can do something straight away. Everything takes time and really takes it out of the people actually doing the processing. It takes a lot of time, and so there's a detailed procedure that we have to follow, but it's worth it in the end.
So how much material did you get?
So we finally released in the beginning of February that we have about 121 grams of material that was returned from asteroid Bennu, and that's twice, so double the amount that the mission was required to bring back. So we doubled what we expected, and so that's great. That means our science team get access to the material we had planned to do our analyses with, but more importantly, it means that there'll be more material available for the rest of the community and for generations of new students and new people who are kids today or not even born yet, to study in the future.
But still, when I hear 120 grams, that's not much, isn't it?
To a sample scientist, that's a lot of material. We have decades worth of material to work on.
You are one of the lead scientists for the OSIRIS-REx samples. So what exactly is your job?
So in addition to analyzing the sample myself, I'm being involved in several coordinated efforts to analyze particular samples at the University of Arizona and in the US. I'm also in charge of or managing a group of scientists from across the world. So there's about 60 scientists in the group all over the world, including here in Switzerland at ETH, making measurements of the sample. And so it's all about coordinating those measurements, making sure we're telling a coherent story, making sure we're doing the best science we can with this really precious material.
But for people who don't know how your work really goes on, how do you analyze this material?
So we use a variety of analytical techniques, so anywhere from burning the sample to digesting the sample in acids to looking at individual particles in electron or ion beam or optical microscopes. We can also take slices of material. There's lots of different ways that we can analyze these materials, and we really want to get to what is the chemistry of these materials, their mineralogy, so what minerals do they contain, how much water do they contain, their noble gases, their age, So with these samples and the different types of analyses we do, we go from what happened to the sample in the curation facility, what happened when the spacecraft actually collected the sample, what happened to Bennu's surface to make it the way it is today, and even all the way back to what were the initial constituents of Bennu, some of which are not even from our solar system. They're actually predate our solar system and are pieces of dust that came from stars that have been long dead. So we're able to piece together that entire pre-Bennu history, pre-parent body history, pre-solar history, all the way through to the geologic processes that happened all the way through to the present day, with the wealth of techniques and expertise on the team.
So for this short period, you already could unlock some secrets?
Yes.
What were the biggest?
So the biggest so far are the bulk chemical analyses we've been able to do on the sample. And what that means is we're looking at the abundances of different elements. And as a cosmochemist, that's really important because the chemistry really tells us what the building blocks of different celestial bodies are. And one thing as sample scientists or cosmochemists that we like to refer to is the composition of our solar system, which is represented in a lot of ways, in most elements, by the composition of the sun's photosphere. And so there's a group of meteorites, it's quite a small group, but we think they represent that solar composition. But what we're seeing from the Bennu samples is that they might be an even better representation of that solar composition. And so it's giving us new hints as to what that chemistry might actually be, and that's important because it becomes a new reference material with which we refer all of the other materials in our solar system to. So that's just one highlight from the material we've looked at so far.
But Bennu is one of a million of asteroids in the solar system. The Japanese brought back from Ryugu, another asteroid, some samples with the Hayabusa 2 mission. Are you able to compare both samples? We do
indeed. So not only do we compare to those meteorites that I mentioned a moment ago, we also compare to the Ryugu analyses. And it's interesting because spectroscopically, so from ground-based telescopes and also from the orbital campaigns around both asteroids, they look a little different. They're both carbon-rich, they're hydrated, but to different degrees. What's interesting about looking at the samples is they look very similar in a lot of ways, at least from the initial analyses we've been able to do. Whereas for a lot of the elements, they're the same, but for the most volatile elements, so those elements that would really prefer to be in the gas phase, that we find actually in the sample itself, those tend to be more enriched in the Bennu samples than in the Ryugu samples. And we're still trying to work out why exactly that might be. We have a little bit more sample than was brought back by the Hayabusa 2 team. So we're going to exploit that extra material to really dig into the fine details of the Bennu samples.
Very interesting. But you're not only working on asteroid samples,
no.
Right? You are principal investigator on Apollo 17 lunar samples that were newly opened.
Correct, yes.
So what exactly are these samples?
So in 2018, NASA announced that ahead of the 50th anniversary of Apollo 11, they were going to make available to the scientific community some samples that they had specially stored away, so had never been studied before. Those samples included some samples that had been frozen, some samples that had been stored in helium gas, so in inert gas, and some that had never been opened. So they were either core tubes or samples that had just been locked away and never looked at. And so it's part of the Apollo Next Generation Sample Analysis Program. And so as part of that, we were given access to some of the most precious samples in the world that had never been looked at before.
So how exciting is it to work with such
Very,
precious
you can see
things?
the smile on my face. Very exciting. And to look at something that no one else has ever looked at before and kind of be the first to make measurements and piece together a sample's history is really important and humbling. And more than that, personally, to give that experience to a student who's just starting their PhD and just getting started, it's almost too much, but really special to be able to give that opportunity and have those students working alongside us.
Over 50 years ago, Apollo 17 astronauts Gene Cernan and Harrison Schmitt brought those samples back. All over the Apollo missions, there were like 350 kilograms, I think it was, of samples. So how significant are these samples now you are looking at?
So what's changed since Apollo to now is technology. So we have technologies that couldn't have even been dreamed about 50 years ago, and we're able to now apply those technologies to samples that were brought back but never studied, and ask new questions of those samples, ones that maybe hadn't been thought about, but since we've had 50 years of technological development and 50 years working on Apollo samples that were available for study, we have these new questions to ask. And so I think these samples are as important back then as they are today, and they will continue to be important into the future as we look to Artemis and other lunar missions.
So Harrison Schmitt was one of the two astronauts. He was the only scientist on the moon.
Yep.
And he worked with things like, we have here an example, one of these sample collection bags. So they had these on the moon, putting in stuff, and they also have had these big bags here where they put the samples. So it must be exciting to be on the moon doing that.
I imagine so, yes.
So have you ever had the opportunity to meet Harrison Schmitt?
I have, yes. So Jack Schmitt is also a team member of the Apollo Next Generation Sample Analysis Program, and specifically was involved in the double drive tube, so this core sample that we had access to as part of this program. And so I met him actually at the very first team meeting that we had for the ANCSA program right before the pandemic. And it was a great experience.
Is there anything special you remember about Harrison Schmitt?
I remember him being very kind and nice and interested, wanted to learn. I study volcanic eruptions. When I'm talking about the moon, I'm talking about ancient volcanic eruptions. And he was very excited to talk about the science that we had planned and that we wanted to do. And it's very strange talking to the person who collected your sample on the moon and they remember doing it. It's kind of surreal.
I can imagine. So what kind of material is it? Are these rocks or is it dust? Is it from core samples? What is it exactly?
So as part of the team, we were initially able to, what we proposed to look at were the volcanic samples. So this is a sample that was chipped from a boulder along with 3 other samples. Those 3 samples were kept under normal conditions, but one sample was kept frozen at minus 20 degrees Celsius for 50 years. And that's the one we wanted to understand how it formed, all the way from the magma that it would have formed from, to its volcanic eruption, to interaction with the space environment. But we were also able, as part of the program, to have access to the core sample. And so that's a mixture of chunks of lots of different types of rocks, volcanic rocks, impact rocks, and also lots of dust. And so that's been really exciting to kind of tease apart the story that core tube has to tell us as well.
So, and what's the scientific focus when you work with that samples?
So my group's focused on looking at the volcanic samples, so really understanding and tying together their magmatic history, so what happened to them when they partially melted and they were rising to the surface, how they erupted, what their chemistry is, are they related to each other, and then also their age. So we're looking at the crystallization age when they solidified, but then also how long have they been exposed at the lunar surface. So trying to pull all of that together to get a really nice history for those samples.
And you have already results?
We have some, yes. So some of the most exciting work we've been doing has been something novel, where we've been comparing the chemistry and the mineralogy of samples in their 2D form, which is how we normally study these types of rocks, but comparing that to their 3D morphology of the minerals and the spaces in between the minerals. And you can kind of think of it as like an X-ray, but for rocks. So it doesn't hurt the rocks, you don't need to worry about that. But doing that and combining the 2-dimensional and 3-dimensional gives us a new understanding of where those samples come from, and we can use lessons learned from looking at terrestrial, so earth-based volcanoes and the rocks they form, to not only understand if the 4 samples we've been looking at are the same, but also where in a lava flow would they have formed. So that's been something really exciting that we just published.
NASA is now planning missions to the moon, Artemis program. Those missions are supposed to land near the south pole of the moon. So how interesting would it be to obtain some samples from there?
Very. I'm very excited by the prospect of Artemis 3 bringing samples from the South Pole, and possibly Artemis 4, 5 and beyond bringing ices from the lunar South Pole. So yeah, very interested to learn more about what those types of samples might be and what they can tell us about the history of the moon. Because they're coming from the South Pole, which has one of the biggest impact basins in our solar system. And so better knowing the age of that impact basin helps us better understand the entire age history, not only of the moon, but because we use the cratering history of the lunar surface to understand every other surface in the solar system, it has knock-on implications, not just for the moon, but for everywhere else we want to go.
Very interesting. So if NASA would call you today to say, hey, we have a seat for you in a capsule, would you go to the moon?
If they would sedate me, yes, because I'm not too good with flying, but I'm more than happy to stay on Earth and analyze anything they bring back.
Speaking of staying on Earth, you are now in Switzerland for a short stay. You are a visiting scholar. with the NCCR Planet in Switzerland. So how important is the collaboration with your Swiss colleagues?
Very, very important. I have two colleagues that are based at ETH that work on the OSIRIS-REx mission, and it's been wonderful getting to know them better and solidify our plans to analyze the OSIRIS-REx samples, and then to meet new colleagues and new people at the University of Bern and ETH has been really wonderful. I can see different collaborations that could happen into the future, so it's been absolutely wonderful.
Thank you very much, Jess. It's amazing to talk with you about all these fascinating things you do. And I wish you good luck with all the missions and the examinations you do. Thank you very much.
Thank you.
So that was our special edition of Space Talk. I hope you enjoyed it. And maybe next time when you look up in the sky and you see the moon, you think of Jessica Barnes and her work. Thank you very much and goodbye.